We're getting it. And I figured out that this camera back here, the self view, gives me the best because of me being able to see, shows me the best of what you're seeing. Because that for me is just too far away. I vision issues. Yeah, this monitor itself it gives me. So when I'm focused on the board, I'll look at your part just gives me the idea of what the students and are seeing.
Right.
Yes, I can see that. Sorry. I'm leaving today.
Well, like I said, originally, I think you told me something. I had put an event on my calendar. I had it for like the 7th and 8th. And you sent me 6th and 7th. I thought you sent it. But
Yeah.
I had it wrong.
And probably what it was I blocked it on my calendar to leave this day, which, you know.
I meant to call you yesterday. I thought
Hey, how are you doing? Good, there you go.
Good.
Good. We don't see you in this building a lot. I come back
Following me
this way.
around.
You follow Jim around? I got to keep Jim straight.
This weekend,
That's a full-time job right there. Yeah, Pat told me I had to keep him straight. You got a Girl Scout this day. Yeah, Scout Taylor.
I know there's a best full of food in our class. Somebody needs to get out of it.
Okay, that nails I'll go get it.
I tried to do something. It's already
You talking about 108 or?
no 136 our class.
Okay. All right.
I saw it early this morning when I watched it.
All right, you are getting it.
Thank you.
See, I'm working on that certificate thing with the wireless. That's why it's here is not working. Yes, we are, but it's weird how we do this. You have to go into secure and remove the validate check mark from the settings. Yeah, and I've got it on my phone where I just need to.
I was going to say, I was going to call you yesterday after she used to say, hey, is anything weird? I need to know if I can do it or whatever. And I got busy and forgot it.
Yeah. Really, things are going really smoothly. I wrote up the steps for Dale to get videos drug over to the Moodle. And it's not hard, it's just a series of steps. But the videos to the NCS series to have to use Silverline to view. So I'm not putting them directly in YouTube. So that, you know.
And yesterday, there was a copy of Facebook now has the peer version of the line.
On Facebook? How cool. Yeah, I haven't been on Facebook yet.
All the way around. Rolling with us, which is everything we can do.
The yeah, it's I got the I run the enrollment stuff for Data Hub and the I ran the numbers yesterday, because we were hoping for it, but we're actually about, because we run it based on student bodies and then based on enrollments. And if like one student enrollment, four student enrollment, same student enrollment, which is two. Yes, FTE. So, looking at data hub, we're down in bodies, and this is not including the minutes, but we're down in bodies by about 15. We're up in enrollments by about 100. So we've got fewer students taking more classes. That's what I would think. I can't remember exactly. I'm trying to calculate what I'm calculating, but who knows what it's like the old accountant joke. What do you want it to be? You know as well as I do as a computer person, you can't have 3 orders and come up with I don't know. It's been down. Which is what it's not. Maybe it was 5. Yeah.
Plug it back in, push the reset button.
Oh.
And they can set up a time.
Ours is exactly
You went ahead and changed.
I finally got into it with the wire cable, and I'm like, yeah, it is messed up.
Yeah, I could. That's when a faculty were talking. Like, oh, my grade book and meeting is broke. I'm like, yeah, but yesterday, when I got back to my office,
So I just realized it's September. I just realized that it's September. And college applications are due in October.
We're not on the states,
Not
just states.
that's good.
But then when I care about.
Yeah, same. That's literally the only one I'm really, if I don't get into it, I'm
That's
probably
the
not gonna
only-
go to the other place.
Sarah just doesn't go to college.
Why is it looking at me
See,
right
the
now?
problem is, I'm only
Applying to state scholarships.
Did you get it?
I think so.
If I don't get into state, I'm gonna have to pay full credit for anything. I gotta be
a 0.
Joe, are you there?
Oh wait, no, there's
I got a 0 on the
Joe?
chart.
We're here. Yeah, can you see
Are
us?
you looking at the class or are you looking at me?
I'm looking at you.
Okay. What do I do to make this not me?
Just
Uh,
the time right
move
now.
all the students to the front of the class.
What?
So they'll give me suggestions on how to make it not together.
She needs to switch cameras.
Can you switch cameras?
You got a Polycom unit.
Yeah, I think they have Polycom.
Did that
Yeah,
switch
there you
it?
go.
Yeah, that's good.
Thank you.
See, Jim, there you go.
It goes into our percentage.
I'll go back today for my check on my.
No, I mean, I think that.
I sent Jim the e-bike with the wrong thing, so. You'll be here tomorrow too, though.
They're tomorrow too. If you got an important meeting, I don't need those words big go out. Ready.
Oh, good.
whatsoever. But
I saw it. I had talked to Rob.
Sammy said she got the same amount. There's something about this.
I got the
one
same
did
one.
wrong.
Yeah.
Something I forgot.
It's a different number.
Well, no, this also works. There's like multiple, but there's something I forgot to do.
Oh,
Like
it didn't
repeating
work.
it.
Like upstairs.
Well, there's like repeating intervals of it from where it worked, but I didn't put that.
so I would have an 88 if you added onto the final percentage for you now.
I was.
Oh. So Raisin wants us to do the free lab stuff that we can already get done during the hour after this class.
And I think that was from the prior meeting.
If you guys tend to this value. I think you chose.
Shows up yet?
All we have to do is, because Sarah Kilgore has in charge of that. All we have to do is put it in separate.
You go, Sammy.
I'm a little nervous.
College
I really hope we don't.
I knew that, and my doing, because Sarah's.
We're talking
Yeah,
about
we
that.
haven't
Will
made
we?
that.
Yeah.
If you wanna get into that,
It's not
get
like
into Stanford and
the
Collegeville for
SGA
fine
changes
tooth,
the
we'll talk now.
thing, we just plan like semi-formal and stuff.
Yeah.
So it's not like you have anything to talk about.
Have either of you started?
And I granted, I know that I'm green, I know I'm
Yeah,
president.
British.
You go, Sammy.
I'm always like, but,
Probably not.
Like, it's not that bad, but then tonight I'm gonna kill myself.
I read the question.
Yeah, maybe 2 pages is pretty good.
Yeah, well, last night was rough for me, so I need to.
Alright. I'm gonna spend it like 10 o'clock.
I got home from Winston, I went to bed
Yeah,
at like
Winston's-
7. I got out of bed at like 7:30 and it fell on.
October the 16th.
Did you do any
12:30, not 1. Oh yeah, I did my homework after I'd woken back up. Because it only took like
Here
5
comes.
minutes. Yeah, this is like 5 to 10 minutes.
I did, you like to see.
Shows up before, is it?
Nice.
Sherlock Holmes.
It's the other fandom.
I'm gonna talk this one.
Supernatural. See the wing at the house.
Can we go outside of arts and sciences?
Well, just, I work translated, which is,
Best app in the world.
I want to have
You know, when the plane flies over your house, you can click on the plane.
That's
Huh.
it.
What's it called?
Yeah, I go, that's when I go to those.
I was thinking so.
And I'll be increasing their own. Yeah.
Look at this.
Why is that tonight?
Now, some people, I don't know if
I
Charlotte
can't
does.
go all the times, so I know they'll try to.
Understand.
I know AX does it.
Because you don't understand.
Like,
Yeah, let me talk with some of the guys over in Business Sciences to see if they have 100% online students who would be really,
Probably not like that, but I will ask.
I
yeah,
sent an email to Maureen and asked her about it.
good idea, yeah.
LAX.
I got half mine, it's just.
LAX is, look at
So
that.
are you
There's
For a work study that can meet
Well,
with
see,
these
I
classes.
might be like slightly confused, right?
So we're having problems in your class.
Most of us are at the top rate, so. I had an intention schedule. All of them applied stuff.
and how do I know exactly?
How did it load? We have to all do that at a certain time because of high school. Anyway, so limited staff, that's limiting some of our.
All the terminals and
Really simple, isn't it?
I just don't understand.
So,
for hangers and stuff.
hopefully you find someone.
How cool is that?
There's no way to do this.
No, I guess.
Oh, I guess that would make sense.
Probably.
Is Angela Reed available during that time?
I'll have to ask.
I want to say Air Force One.
I mean, this semester we're covered, the next semester.
But,
I've got one poll.
I have a friend,
No,
one that I,
one of them, right?
he flies out of the Winston-Salem Airport. So I can go there, click on the airport.
Did you guys
He
see
flies
his
for
right
budget, so one of those is
Yeah.
Oh, wow.
How cool is that?
It's almost
I
like
just
gone,
won't
right?
stop.
Wait, there's an airport.
Yeah, it's really frustrating.
Yeah, it's not an
It's really
international
small.
airport, it's literally just for private business.
You know how, like,
Just like Advance has that.
KH2.
Chip's is the only one that uses it.
It's like
I need to,
that way.
and I don't
No,
care
you
about
wanna
the
say
rest.
something serious?
Yeah.
A shadow, and it's actually
So you can find an advance.
No.
Wait, there's
He
some-
was all up to the assignment.
Is it like,
Sydney, Dylan, Josh, Carson is Carson. Davis. Can you hear me, Davis?
Yes.
Carson's not there. Like, Rezo,
Seat, Kyle.
these are not there.
Big Bird gets the wall seat.
Oh, I will never get that
look
seat.
at that air traffic.
I think you get that was kind you have to admit.
To Charlotte.
I like the new haircut.
Yeah.
I
What about this place?
to get something about it.
It's
Um,
It's American.
so first thing, you need, let's go over that, handout that you had yesterday, just real quickly. Hopefully it wasn't too difficult.
Here, Carson, grab this.
So, what about number one? Find a maximum delta for number one? Come up with.
We have a question, Dale.
Yes. My
So
question,
I
Kyle?
talked. Yeah, I have a question. So I talked to a couple Davidson campus students, and we just have a question about, we don't really understand what exactly we're supposed to be looking for and exactly how to get there. Does that make sense?
Well, yeah. You're supposed to be looking for, according to the handout, have an epsilon value that constrains y dimension, and then you want to find a delta value that constrains the x dimension, so that all of the ordered pairs of the function are within the rectangle created by the delta dimension and your epsilon dimension. So we want all ordered pairs in that window. So whatever the function graph looks like, you have a delta direction in the horizontal, and you have an epsilon amount in the vertical. So this center point would be like your limit value, and this center point would be your x, your c value we've been using. And the end would be c plus delta, and the beginning would be c minus delta. And the vertical direction, you would have L minus epsilon and L plus epsilon. And so you want to force to be within this horizontal window. That's what you're constrained by that. The graph is doing something in that horizontal window, but you want to be close enough to the C value so that all of your order pairs that go with that function are within the horizontal window. So you have to get close enough to C so that, like if I have a graph that, if I had a function that did something like this, then all of the values of all of the ordered pairs that are xy between here and here, all of those xy ordered pairs are in my viewing window. But out here, I have some x coordinates whose y coordinate is not in the viewing window. So I'm not close enough in to make sure that all of these ordered pairs in this interval are in that interval. So I would have to shrink my interval down. If I shrunk my interval down, you know, I keep this interval the same, but if I shrunk my horizontal interval down to say there, so this would be my delta and this would be my delta. Now you see that in this new window, this green window, all of the ordered pairs on the red line are now inside that window. Every x value in this right here has a y value in the window. So that's the objective, is to find a horizontal dimension so that your input values are controlled sufficiently that the output values land in the prescribed window. So you're given a prescribed horizontal, prescribed vertical dimension, and you have to find you get to determine, figure out, calculate a horizontal dimension that makes it look like that. We can also talk about doing this without a calculator, I mean, without looking at the graph. I was just asking you to look at the graph and just guess delta values. I suggested just guess and check. We did yesterday. Just given epsilon is 0.01 or whatever, guess a delta value and create a window and look at it. And does it go through, does it look like it's going through the corners? Or at worst, you can have one corner and one side, but you never want something going out the top and bottom. Like this first window here, this graph went out the bottom, so I had x values whose y values were outside the window. But if I have it going through the corner or through a side, then I'll be good. So we did that just graphically with the calculator, just guess and check. But we don't have to guess and check. We have algebra skills we can employ, but we can practice that. So let's try it with that algebra game as well. Let's see. Okay, how about an example? Let's say that epsilon, given epsilon equals 0.1, and you find the maximum delta possible that satisfies the definition of this statement right here. And the statement of the definition was, again, for any epsilon that I can give you, I should be able to find at least one delta, if not lots of them, that constrains my inputs so that the outputs are within that epsilon window. So I've got an epsilon window given, and I want to find a delta amount that constrains my input so the output is within the tolerance I'm allowed. So I can do this algebraically rather than by graph. We did it yesterday by graph. We just guessed and checked. We made a graph of this. Y'all remember doing this? We made a graph of x squared, and then we set the window, in a vertical dimension. We did something. Yesterday we would have done something like this. Suggestion. Today I'm going to do a little different. So we drew a graph of f of x equals x squared, and we did a zoom standard. So this is standard, and this is what we did yesterday. So you get something that looks like that. And then we said, okay, well, we want to be close to 4 within 0.01. So we would then change our window setting. So this was negative 10 to 10, negative 10 to 10. And then we changed our window setting. So again, what we did yesterday, this was still negative 10 to 10. Now we change this vertical dimension to be close to 4 by amount of 0.01. So we went 4.01, so 4.1 and 3.9. This number is 4. We're centered right at 4. So I still have an axis in here. So I'm really kind of zooming in very close to 2. I'm trying to get close to 2. So I'm worried about here's the 2 and here's a 4. There's something going on right there in my graph. I want to zoom in on that. So I've zoomed in, I put in a horizontal control, if you will. I put a little horizontal control right here. Color. That's these numbers here. And now yesterday I guessed. I said, okay, let me see if I can guess a dimension in the x direction that would get me close. Get everything in the window. So I might say just guessing, maybe I'll get close to 2. So I'm gonna change this from negative 10 to 10. I'm gonna try to guess. I want to get close to 2. So let's say 1.9 and 2.1. And I don't know what the graph's gonna look like, but hopefully, if all is right, hopefully the graph stays within this boundary. But it might not. It might be that it goes, it could be that that's not tight enough. Maybe it does something like that. And if that was the case, if that's what we saw by squeezing into this, into a little box like that real close, if squeezing in real close still had, in this example, what I'm showing, which I haven't graphed it or examined, but I potentially could have x values that these x values map outside of the window. They're up here somewhere, so they're out of my tolerance. So I would have to then shrink my x dimension down further to get it tight enough. So I might have to go even tighter. So maybe I would then do something like this. And this would be my new delta here. And so my window is different to get it down so that all of the x values in this window land in the tolerance that's allowed. Does that ring a bell and make sense to y'all now a little bit? Mm-hmm. Now let's try it one time algebraically, because that was graphically and it was just intended to be kind of a guess and check type of thing. Some of us feel a little more comfortable if we can be more exact. Okay, well let's do it algebraically then. So this is the idea again, same what I'm doing right there. I want to figure out if I want to be this close, what does that mean? What x values are going to make that happen? So one more time, I'm going to think graphically, but I'm going to do it algebraically. So I'm start off with a thinking graphically. I have a curve happening. and I'm getting close to 2. And I want to show that when I get close to 2, that the y value gets close to 4. But I have already prescribed for you a window of epsilon 0.1. So I'm exaggerating my window. This is going to be greatly exaggerated so it shows up. So I have a window this way.
Oh, that's cute.
4.1 and 3.9. So my question is, you need to find for me, we need to figure out some kind of a delta dimension that fits here.
Dang, that's thick.
This is going to be 2 plus delta, and this is going to be 2 minus delta. But the problem is, because this isn't linear, I talked yesterday, if it's a straight line, then it will be symmetric easily, automatically. We need to be symmetric on either side of 2, but because this is curving, it may be that one side is shorter in order to stay within the green box. One side might need to be shorter than the other. So we'll have to take the smaller of the two. So I'm going to call this one, the left side, I'm going to call it delta 1, and the right side, I'm going to call it delta 2, just because they might actually be different. And then I'll choose a delta, a single delta will be chosen. The answer delta will be chosen as the smaller of these two, whichever one, because once I get the smaller, if I got two different numbers that work, if I take the smaller of the two, then both of them will work. I'll show that in a moment. Okay, so let's figure that out. So what I want is, based on this picture, I want the output of that number to be 3.9. Do you all agree with that? This number input with the function has to have that number output. Okay, let's write that down. That means I want the function of 2 minus delta 1 has to equal 3.9. According to that picture, that's exactly what I want. Does everyone agree with that?
Yes.
Isn't y'all agree with that? Okay, good. Well, this is algebra now. I'm not even going to look at it. I'm not going to pull up my graphing calculator. I booted it up just in case, but we won't even look at it. So what does that mean? That means, according to function, you're going to square. So we get the square of 2 minus delta 1 equals 3.9. Can you now easily, from probably 9th grade, solve that for delta 1?
I think I'm kind of stupid.
Thanks, yeah. How do you do that? Take square root of both sides. So 2 minus delta 1 equals the square root of 3.9. Technically, it's plus or minus. Doesn't really matter to me. And then we'll subtract 2. So negative delta 1 equals negative 2 plus minus square root of 3.9. And then delta 1 equals 2 plus or minus square root of 3.9. We'll have to think about which one of those we want.
Wow.
So if I divide by negative, I get a positive 2, and then I still get a plus or minus there. So now, give me a decimal approximation for the, give me 3 decimals approximation.
So that's still algebraic. What? Chicken wing? What did you say? Please,
I follow that?
yeah.
Yeah, we'll do the plus first. Give me the plus.
3, I mean, saying like 3
decimals.
3.9. You know,
And then what's the other one? Yeah.
Go through 5.
Good. Okay, good. Now, let's stop and think about that. That's doing the actual algebra from pre-calculus. You know, you take the square root, you get plus or minus, and subtract and divide by negative. No, I can't have both of those be my delta 1. Only one of those can be my delta 1 is my left side delta. I'm looking just at the left side, then I'll look at the right side in a moment. I haven't done that one. But I can't have both those be the correct answer. Let's think about that. So we're saying we're going to, delta is a distance, We're going to go away from 2 and have x values that get trapped in the window. So looking at this picture, does it seem like that delta would be 3.975? So I'm going to go a distance from here, from there, go a distance of 3.975, which is going to put me way over here. That doesn't seem like the right plan to me. But maybe if I went a distance of 0.025 from 2, went backed up 0.025, then my outputs are going to be stopped in this green window, which is good. So we're going to say that the correct answer for this delta 1 is that one right there.
Okay.
I'm going to repeat the process for the right-hand side. So this is left. Now we're going to do right. Short-circuiting myself a little bit. This is 2 plus delta 2 squared equals 4.1. So I'm repeating, but I've moved off a couple of steps. So delta 2 is going to be plus minus the square root of 4.1 minus 2. So once I just solve my equation real quickly, and then I get 2 answers, and we'll decide which one's probably the correct one for delta 2. We with us, Davidson?
Mm-hmm.
Far so good? So we're trying to find, my objective one more time is to find a singular delta. I have found one that's the left side delta. I'm now going to find another one that's the right side delta, and then we'll decide what's the actual answer. So I get 2 numbers here? Well, dang, I wish I had more decimals, because those came out exactly the same. They shouldn't have. How many, what is it, like, give me 5 decimals for that one, just for the sake of it.
1, 2, 3, 4, 8, 4,
5. And I'm going to gas back here. Somebody give me all 5 decimals. Hold on, give me the other. You got a second one here for this one? Okay. That's too small. Negative something. Okay, so, and then once again, someone real quick, give me the 5 decimals on this one.
0.256.
That? Okay. Now, here's my, so I wanted that because I wanted to show you something. First of all, let's go back to the right side. I'm going to choose that as my delta because, again, using a negative or something, that doesn't make any sense in the world. Delta needs to be a distance, so it certainly shouldn't be negative. And we want a small distance to go across to the right. So we're going to say that delta 2 is 0.02485. And delta 1 is 0.02516. Let's think about that. So I'm going to write that down here. So this delta 1 is, I'm saying I can go this dimension, I'm exaggerating again, by an amount of 0.02516. I can go that direction by an amount of 0.02485. So, think about that for a minute. As long as I'm no further than 0.02516 to the left of 2, every x value will map inside the green window. Were you clear on that? If I'm no further than 0.02516 to the left of the number 2, then every x value in that red bar, every x value in here will map inside the green bars. On the other hand, if I'm no further to the right of 2 than 0.02485, then every X value in that window will map inside the green bars, which is what we want. The question was, though, find a singular max delta. So we're looking for one number. This number right here. Actually, no, this is what we're trying to find. My question is to you, which of these are we going to use?
The bigger one.
Let's put back up. Beep, 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 back up. So, first question. Why are they different? Why are they different?
Is that rhetorical or asking for an answer?
I'm asking a question. Because it's not a straight line, the graph is curved, exactly the right answer. Okay, second, why do you think this number here on the left is actually a little bit bigger than this number on the right? Not rhetorical.
I mean, if the slope is higher,
At least
you gotta
Yeah.
get what? You gotta
That's
get
right. If the slope is steeper, then you got to get closer in to get it to fit. If the slope is less, then you can go further out. Excellent. Adverse rate of change. So, y'all are getting the picture now. Good, good, good. Okay, now the final question. We get to pick, eeny, meeny. So you kind of got to take out your coin, flip it. Which one do you think is the one we're going to pick as the right answer?
Pick the right one. Do the right one.
The smaller
He said flip a
Smaller
coin.
one.
The smaller one.
I'm saying do the right one.
Flip the coin. Razor says pick the right one because he came up heads. Anybody want to vote for the left one because you came up tails? Okay. The right one's going to be correct and
Yes.
not the left one. But why?
Because
Why does that?
Why does smaller matter?
yeah, it's
Back.
smaller, so yeah,
Because if I pick the bigger one on the left side and put it on the right side, my bigger one is going to be out here, and that's going to put me, notice I'm going to have X values that are mapping too high. But if I pick the smaller one, then which is over here, then the left side will be inside, and what will happen is now, by picking the smaller, my graph will be like what I showed, well, over there, kind of. If I pick the smaller one versus the bigger, let's make sure we're clear on that. So, smaller delta. What will happen is the left side will go through a side and the right side will go through the corner. That's okay. If you pick the larger, then what will happen is the left side will go through the corner, but the right side will go through the top. That's not okay. Y'all follow that thinking?
Mm-hmm.
So what I'm saying here is I went out the same amount on either side of 2. I went 0.2516 on either side. If I go that far to the right, the left side will be okay. But if I go that far on the right, then I'll be too far out and I'll miss some. But if I go the smaller distance of these two, then the smaller will certainly work on the right, but it also will definitely work on the left because this is the worst, and I can do better. So okay. So my answer is the smaller of the two, the 0.02485. So this number is 0.02485.
Yay.
I could have done that by guessing and checking on a calculator until I got my picture to look correct, or I could have done an algebraic. That's what I just.
It's algebra.
Clear now? A little bit more clear?
Mm-hmm.
Al, you asked the question, so I'm going to pick on you. Are you a little more clear now?
Yeah.
Yes, sir. Everyone else a little more clear? Okay. Well, good. That was a good question. Glad you asked. So,
What did he say?
What we were exactly supposed to be finding.
Wow, you're looking for a delta.
Well, obviously I know that.
That looks like a musical.
Yeah, the
It
delta.
also looks like.
on the worksheet, however, the requirement of, like here, I decided on this example, in order to be able to see the real difference in the deltas, I went out to 5 decimals. We weren't asking for necessarily 5 decimals on the worksheet. Because you were doing it with the graphic calculator, I kept it less precise. But if you do it algebraically, it can be more precise. So are we comfortable now going forward with finishing this part 2 worksheet. Didn't already finish. All you have to do is graph it like we did, guess and check. If you want, though, you can sit down and do it algebraically. That's perfect. Good. Now at this point, you need to know. You do both. Like kind of guess and check with the calculator on the graph, and you also need to do it algebraically by solving an algebra equation. Questions on that?
No.
Okay. What about limits that don't exist? I have, I try to go to the left. So we have seen limits not exist for other reasons. What was one way that a limit did not exist that we've seen already? Say louder, Joe.
The limit from the left and the right without using.
Yes. So if the limit x approaches c to the left of f of x is not equal to the limit x approaches c to the right of f of x, then the general limit does not exist. Then we had, this was kind of a comment yesterday, if you have the limit x approaches c from the left of f of x equals infinity, which equals the limit x approaches c from the right of f of x. So both sides are the same, they're both going to infinity. Then we can say limit x approaches c in general, not just from left to right of f of x, equals infinity. But note, this is considered also unique, does not exist. If they both sides go to infinity, you got this asymptote going up to infinity on both sides of it, then we can write that the limit is infinity. That's okay, we accept that, that's no problem. But it's also known that infinity is not a real number, so we say that the limit doesn't exist. So it's kind of this weird gray world where we write that the limit is something, we can also say that the limit does not exist. On the other hand, if the limit x approaches c from the left of f of x, kind of going back up here, if that's equal to infinity, but the limit x approaches c from the right of f of x equals negative infinity, so if the left and the right are going to infinity, but they're the different infinities, then we can't write the limit in general as anything. That's just, so limit x approaches c of f of x definitely does not exist here. So once again, if both sides go to the same infinity, either plus or minus infinity, then the general limit can be written as going to that same infinity, even though technically it does not exist. But if they're going to opposite infinities on either side, then you definitely don't have existence. But there are other reasons that it doesn't exist. We need to explore some of those. So I'm going to go, can we share the computer now? So, for example, let me put into my calculator simple sine of x. Check my mode.
Oh yeah.
I'm in radians, I am in radians. So we're going to go back and do a zoom standard for that. You don't know what sine of x looks like. My question here is, what do you think about the limit as x approaches infinity of sine of x.
Looks like it's fluctuating.
Yes, the sine wave, as you go out to infinity, the sine wave continues to do this. So does the sine wave ever get close to a particular y value? When we want a limit out of infinity, we'll put a horizontal asymptote. We want it to get close to a particular y value. It's always fluctuating, so it never has a limit out of infinity. So we would write, and I don't know if I can do both. Can we do camera and or not? So you would write limit x approaches infinity of sine of x equals d and e, does not exist. And then as an explanation, you would write something like, because it oscillates forever. Now, oscillate, O-S-C-I-L-L-A-T-E-S, oscillates.
Aren't those like cats?
That's an ocelot.
Ocelot.
All right, now, I'll get her to switch back. Switch for me, please. Back over here. Okay, so x approaches infinity of sine of x equals does not exist because oscillates -1 to 1 forever.
Forever.
It never hones in on a single value. Okay, that was interesting. Now let's try another one. Back over here, please, man. I'm going to change my function.
Romeo right there.
I'm going to change to sine of x divided by x.
Oh,
As x divided by x, my new function. We're going to graph it.
We're gonna get straight rational.
Before I graph it, any predictions? What do you think about this?
Predictions?
Yeah, don't do it.
Any prediction, any guesses? Think about taking sine of x, this oscillating sine wave, and now as you go further out, the function you're going to divide by x, always dividing by x. So what's that going to mean? Can you predict?
We're gonna get straight rational. That's what it's gonna be. It's gonna be
No.
rational.
No, I don't know if it's going to be rational. It is called a rational function. No, it's not called a rational function. Why is that not called a rational function?
Is it because it's a polynomial and it needs to have a finite amount of limits on a ratio, but sine doesn't exactly have a finite amount of terms?
You're on the right track there. Sine of x is not a polynomial. We can write it in polynomial like, stay around for count 2, but it'll have infinite terms instead of finite terms.
I was just
It's
guessing.
not really a rational function. Any predictions what it's going to look like? How's it going to affect the behavior of the graph of sine of x when you divide by x?
Well, it can't be 0 now. We know that much.
X cannot be 0. That's a good question. Yeah, good observation. X cannot be 0.
Yay.
So when you divide by x, think about that. So sine wave never gets bigger than plus or minus 1. Here, I'm going to just press graph and then we'll see. So sine wave never gets bigger than plus or minus 1, right?
Yo.
See what happened? See that?
No, I don't. I mean, it just looks like one
Let's see
little.
it. Let me emphasize to you here. So I'm going to go to the middle board. Okay, so sine wave. We all know what the sine wave looks like. Now we're going to look at sine wave divided by x. So think about that for a minute. When x, you said x can't be 0, so what's going to happen? Okay, so we all know the basic sine wave. This is sine of x. Oops, not very good. Okay, my sine wave's getting out of control. You just have to bear with that.
Wow, man.
Okay, so this is just y equals sine of x. So what do you think if I'm going to come in with a different color and do sine of x divided by x? Okay, so we're going to do y equals sine of x divided by x. Well, the first observation was I can't divide by 0. So immediately means I have an open circle at x equals 0. Okay. What about when x is 1? Well, x is 1, then sine of x divided by 1 is going to be sine of 1, whatever that is. Sine of 1 is going to be like about right there. So there's a 1. Okay. And then what? Well, for example, when we get out to about right there, let's think about that point.
That's 2 pi. No.
This is pi over 2. This is pi. This is 3 pi. How big is 3 pi over 2, by the way, folks? Just think about it. How big is 3 pi over 2? As a
2 pi over 2 is just
as a decimal.
pi.
Take out your calculator, dude. 3 times pi divided by 2. Tell me.
3 times pi divided by 2. I couldn't hear the man. I feel bad.
4.71. Okay. So 3 pi over 2 is approximately 4.71. Okay. So we're doing this point right there. We're saying that the sine of that number is -1. Good. But now we're going to take the sine of 4.71 and we're going to divide by 4.71. What do you think that's going to do to the answer? The answer originally was -1. The sine of that number is -1. Now, if I'm going to take -1, I'm going to divide by 4.71. What's going to happen to that final answer?
Is it going to shrink?
A shrink to about -1/4, isn't it? So it's going to be like right in there somewhere.
No, we won't straight truncate in this.
Okay, let's try out here. This point out here that's a little too high, but let's just pretend it's the correct height. That's a height of 1. When is sine back at the height of 1? Well, let's skip that. Let's go back here, right there.
Okay, that's 0.
We got a point. Okay, so sine of 2 pi is 0. But 0 divided, so you're doing sine of 2 pi divided by 2 pi. Well, that's 0 divided by 2 pi, which is 0. So I get, that point is still right there. I'm going to guess that point's still right there, too. What about this one up here? That's up at the P. That's at, let's see, half pi plus 2 pi is what? 5 times pi? 5 times pi. Okay? So what is sine of 5 halves pi is 1, but then we're going to divide by 5 halves pi. How big is 5 halves pi as a decimal? .8. Something. Okay, so I'm going to take number 1, which is right there, and I'm going to divide by 7.8, which is going to put me at about 1/8. That's like real close right there. So what's happening, folks, is the graph is going to do something like an open circle right there. It's going to go down, and it's going to start waving at you, but the waves are going to get ever less smaller.
Also shrinking.
Yeah, they're going to get, we call it damped, called a damped sine wave. Stick around for different equations. We'll get in a lot of detail about damped sine waves. Graph on the other side, what happens? I'm going to divide by a negative value. So this sine value here is going to get not only shrunk, but reflected because I'm dividing by a negative x value. X is now negative. So my graph is going to become actually become an even function. It's going to be a symmetric value. So that's going to go 0 there, something like that. It's going to wave. It's just going to, it's going to be on the other side of the y-axis, and there's going to be a hole right at x equals 0. So we could say on this picture, we could say some things about the limit. The limit x approaches 0 of sine of x divided by x, what do you think that is? As x approaches 0, look at the green picture of that. It's 1.
Yeah. Right.
Now, that's a curious thing, folks. Remember, yesterday we had these missing points for one reason, now we have them another. I can't use 0 in the function sine of x over x. In fact, if you tried to plug in 0 into that function, what would you get?
Undefined.
You get sine of 0 divided by 0. What is sine of 0?
Wait,
Sine of 0 is 0. So if you decided to try to plug 0 into this green function, you get 0 divided by 0. In high school, you said it's undefined, you just went on. Well, we're saying if you're close enough to it, that the answer is 1. So that's going to blow some minds later on as we go further. So keep that in mind right now. We're going to start allowing to divide by 0, and it's going to turn out that 0 divided by 0 isn't always what you think it is. Okay, what else, though, we can say on this? We just mentioned earlier the limit x goes to infinity of sine of x over x. What do you visually see there?
It's 0.
That's getting close to 0. The sine wave is being damped down, so even though it's oscillating back and forth, it's still oscillating forever, but the oscillation heights are become amplitudes, getting smaller and smaller, so that it's getting damped down to getting close to 0. So the limit at infinity is 0. Here's another one to examine. How much time? Here's another one that's kind of curious. Okay, so this time I'm going to put the parentheses. Oops, that's a little light. So that's the 1.
Oh, dang, is it going to do it?
We're going to put the parentheses outside. So I'm doing now the sine of 1 over x. Parentheses 1 over x. Let me see if I can graph this. Let me zoom in one time just to see what it looks like for a close range.
That's deep. Yo, that's an N.
No, that is good.
Looks like an N, doesn't it?
Yeah.
So when you look at that picture zoomed in, I didn't look this right, I'm sorry. So when you look at that picture, we're able to say, yeah, it looks like an N. And what I'm seeing, what I was seeing is the graph. Make sure I get it right. Okay, so it kind of comes in from below, crosses, and then that's it. Okay, so it comes in kind of like this, and then it seems like it crosses, and it looks like it comes back down there, and then on the other side of the axis, the y-axis, looks like it kind of comes down in here, and then does this, goes up a ways, and then comes back down like that. Is that what we saw on the calculator?
Yeah.
Try it on your own calculator. I encourage you to do that. Do that as we do this game. Make sure you're in radian mode, of course, because remember, radians and reals and degrees are for dummies. Calculus.
I didn't understand the latter half. You said radians are real.
Radians are for real and
degrees are for
dummies.
Now, we've used degrees occasionally, but in calculus, you'll want to switch them to radians because okay, so let's zoom in one more time. We'll play that game like, okay, we want to see what's happening. If we get our tolerance down small in the y direction and our x, I'm going to zoom in again. So I'm just one more zoom. Zoom in, which is zoom in as a 2. We'll zoom right back at the center of the whole graph. Now what do we see happen? Oh, wow.
Oh, dang. That looks like a lot of it.
Now, what do you observe? I got closer to the origin, but instead of looking like it kind of made an N, as Grazo observed, instead of looking like it made an N, now it looks like, as I've zoomed in tighter, so I've got a tighter window. It's still kind of doing this, but all of a sudden in here it's going, and it looks like it's a bunch of stuff that's going outside my window. You notice several X values that have Y values outside of the window. That's not good. I need them all, in order for the limit to exist, I need to be able to get an X dimension small enough that the Y dimension stays in my tolerance. That was the whole game we were playing. So let's zoom in one more time. See if we get down tight enough that we can really tighten it up and get it back, behaving well.
Dang.
Wait a minute. Now I've got even more of them going outside the window. What's going on here? I'm going to zoom in one more time.
Oh,
Hey, I have a barcode happening now.
it's a barcode. There's a secret to this, I swear, there's a conspiracy.
How do we explain this? What's really happening? Why is it doing that? Okay, so once more, we have the regular sine wave. We know what a regular sine wave looks like. We learned that a long time ago. But we're now doing y equals sine of 1 over x. What is that going to do for me? So, first of all, I cannot let x be 0, because if I have 0, I get 1 divided by 0, and we know we can't do that. But what about other values? Okay? Well, because this is a reciprocal, and what it's doing is, if you go out here to the number 1, brought to the number 1, so there's the number 1, then everything to the right of number 1, so bigger than 1, let's think about that, the reciprocal of that. So think about an x bigger than 1, like x is 5. What's the reciprocal of 5? Reciprocal of 5 is 1/5. So you're going to go back to 1/5 and find the sine of it. Well, the sine of 1/5 is like right there. What if you go out to 100? X equals 100. What's the reciprocal of 100?
1 over 100.
1 over 100. 1 over 100 is way back over here somewhere close to 0, and the sine of 1 over 100 is right there. So what's happening is everything,
It's gotta be G.
there's 1, everything of the sine wave that's outside of 1 now gets mapped between 0 and 1. So all of these infinite waves are now, so 1 starts about there, and goes up, and then all infinite waves between 0 and 1, or the tail of the sine graph is now squished between 0 and 1. While, again, by the reciprocal, everything between 0 and 1 gets mapped out there. So this little bit of curve, it now gets kind of spread out from, was 0 and 1, now it's spread out from 1 to infinity. And on the other side, it's the same idea. The other side is going to be similar. You're going to have, between -1 and 0, you're going to have all these barcode-looking waves going up and down, infinite waves going up and down, and then eventually it kind of just feathers out to an aspect. So what do we say about this one? What kind of statements do we write? How about
0.
limit x goes to infinity of sine of 1 over x? Looking at that graph, what we just discussed, what would you say the limit as x goes to infinity of the sine of 1 over x is?
Still 0?
It's 0, that's correct.
Okay.
So when we go out to the ends of the graph this way, the y value is getting very close to 0, stabilizing out as a horizontal asymptote of 0. However, what about limit x goes to 0? So when we get close to 0 from both sides, what do you observe happening? As I'm coming in from both sides on this curve, I'm looking at all of these infinite waves going back and forth. So it's like, as your fingers come towards the origin, they start doing this, back and forth, like a giant sewing machine or something. They never get close to each other, except for when they're just going flying by momentarily, but they never stay there. And so we say that the limit doesn't exist because it's just flat crazy.
Danny goes crazy.
Just flat crazy.
Yeah, bro.
Use oscillation again. It's a different kind of oscillation, but we'll call it oscillation again.
It's like a microscopic isolation.
Okay.
I can't.
Okay, so we need to take a moment and talk. I guess we got like 5 minutes. 3 minutes. Okay. You were asked last night to read section 1.2 and try number 1, I believe. So let's take a moment now that we kind of done a little more talking about some of the details. I haven't gone over all the definitions in the book, but they're all there, and you need to understand them. We'll get more detail tomorrow with some of the definitions. But for now, just how we've done. Let's take a look at problem 1 on page 97, and we'll play the same game again. Volunteer to read it, and then explain it. So. Volunteer for 1A. Yeah, I see it. Hang on. See a hand up, Mason. You had your hand up, right?
Yes. Okay, true or false? For limit as x approaches c of f of x to be defined, the function f must be defined at x equals c, and I put that as false. X equals c can be undefined, and there can still be a defined limit. Like x of c does not have to be defined for there to be a defined limit at x equals c.
Right, and that's exactly right. And why is that? Because the definition stated involves a punctured interval. Remember that? It had this missing point. So simply based on the definition, you don't have to have a value at x equals c. Absolutely right. Good. How about 1B? A volunteer? Or you got military style? Chloe, could you take 1B, please?
Sure. True or false? We can calculate a limit of the form f, the limit of f of x as x approaches c simply by finding f of c. And I got that was false. One example where this wouldn't work is that if c was equal to infinity, then you can't plug in infinity as a value for f of x because it's not a definite value and you can't calculate it.
Absolutely. Also, here's another couple of examples. This one, you can't plug 0 into that function, but yet the limit is, you can't plug 0 into the function, but the limit is 1. You can't plug 0 into this function, but the limit does not exist. So lots of examples. You're absolutely right. You can't plug infinity in because it's not a real number. And other times you can't use it because it's not in the domain. How about C? Joe, you going to take that?
Limit of f of x versus c equals 10, then f of c equals 10. Good, false.
False what? Same thing. That's right. I mean, again, I can't plug in a 0 to either of these functions, and there's no point on the graph that I can point to and say, oh, look, there's f of c, f of 0. So same thing here. Not guaranteed. It might be, but it's not guaranteed. Okay, D. Aggie said she volunteered. Good, thank you.
Sure, also. F of c.
Same thing. Yeah, we saw. Didn't we draw an example yesterday, Rezo and Joe, where you had to put a point on the graph? Don't remember that? And the limit as x approached c. So you had this point there, but what was the limit? It went up to infinity and negatively. So just because there's a point in the graph doesn't mean the limit is the same. We saw that example yesterday. Okay, good. E. Who's going to volunteer? Someone Davis. Carson, you take it?
Yeah. E, right? True or false? A function can approach more than one limit as x approaches c. And that is true, and I think we had like one that goes towards positive infinity and towards negative infinity as an example earlier. So those
Well,
would be,
okay, from the left and from the right you can code it two different values, but they didn't say from the left and right. So I see what you're saying. If I go from the left and from the right, I can go to two different values. But they didn't say that. They were saying at C, going to C. So you can't, if I talk just C and not from one side, then I have to think both sides at the same time. If there's a limit, if there's a limit at C, then that has to be the same number. I can't go to two different numbers. I think the answer there should be false. You can do from one side and get two different numbers, but not just in general approaching C. Okay, yeah. Thank you, Jim.
True or false? Limit f of x, x approaches 4 equals 10. Then we can make f of x as close to 4 to 3 as we like by choosing values of x sufficiently close to 2. And also that was false. I just flipped it around. F of x equals 2, x equals 4.
Right. They just switched up their x's and y's, right? So if they hadn't, then it would have been true, but they switched them up. Good. Should catch on that. G. Brittany, can you take that, please?
True or false? If the limit of f of x as x approaches 6 equals infinity, then we can make f of x as large as we like by choosing values of x sufficiently close to 6. And I said true, as x approaches 6, the f of x keeps getting larger since it's going to infinity.
Right. That's exactly the idea. We haven't done any going to infinity. We've done the windows, the graphical windows with a finite number as the limit, but the same idea happens for an infinite limit. The idea is instead of a horizontal window like this, where you've got a top and a bottom, if you're saying that the whole thing is going to infinity, then you just simply have a bottom, and you need to be able to get close enough to 6 to put everything above that bottom. There's no cap on the top because it's going to infinity. So yeah, that's exactly true. You're right. And last one, H, volunteer real quick. Al, could you take that, please?
If the limit of f of x as x approaches infinity equals 100, then we find values of f of x between 99.9 and 100.1 by choosing values of x that are sufficiently large. I put true.
That's true, and that's the same idea. We're getting close to a fixed value of 100, but instead of being close to a fixed number of c, we're going out to infinity, so we got to be able to go far enough out the number line so that we get close to the asymptote. Much like this sine wave that's getting damped, we have to go far enough out to get close. If I say I want to be this close to the line, the asymptote, then I have to go far enough out. If I only need to be that close, then I can be not as far out the x-axis. But depending on how tight I want to be towards my asymptote, you have to be able to go far enough out to get there. That's what this statement is saying. That's the idea. Okay, so for homework, finish the handout if you haven't already finished it. I will post, hopefully it's right after class, an assignment in section 1.2. I didn't get to it yesterday. And work on that as well. And then I'll see you tomorrow to finish up, clean up, and get number 1.3.
Hey, Brittany, what do you want to work on? The lounge or? I mean, I don't go there. Starting at 10:30. I mean, I'm not that.
Amanda?
Yes. And we're going to test to see if we can do a sheriff's PC and share the board from this side simultaneously, okay?
Okay.
Okay, so right now, we're gonna send the room PC that has the calculator on it. Okay, and
You see the calculator on one screen and the camera still on another.
Yeah, I'm seeing calculator and the whiteboard on two different screens.
wait, Dale, wait. You see Dale?
Yeah.
Got a Google Feed, so they.
So what we're seeing as a minor picture is that if
They
we're
have
seeing
to
as two
camera.
screens.
So what we'll do then is when you want to do this, we'll show that view and then just pick a board. Okay, and you focus in on it, and then I will show that, and in that way they'll see both simultaneously.
I won't do that, I'll try to keep it on the center board.
Okay, yeah, okay, good.
Why do you have
Unless you're both.
this restricted?
You're basically showing that there are more values in here other than just 2 that make it correct. Like, you're basically proving that the answer is 2. Or 4.
But why does it matter? Okay, because he had shown a picture where this had like cut down over here. How is that wrong compared to, you know, like?
Because the goal is to make sure that you have every single X value accounted for. So every single input in your area has an output.
So really, you can pick any area.
Yeah, I mean, generally, so you're looking at these 2 numbers, right? 6 is going to be the Y value here, and
Okay.
1 is going to be the X value here.
Oh, okay. That
You see
makes,
what I'm
yeah, okay. But like, so,
So like over here, it's the limit as X approaches 1, so 1 would be right here. And f of X is equal to 2, so 2 would be here.
okay.
So it's not just like arbitrary, you're still following the definition. So like down here, like you're gonna graph the original,
Yeah.
right? And once you graph that, so like if you see the original looks like this. So you're gonna graph it, you have this 10 by 10 window, right? And you have sine of X. So you know sine of X looks like this, right?
Yeah.
And so if you're looking at this at 0.8417, right? So it's like 0.8417. No, check that. That's 1. And 0.8417 is somewhere up here. Right, so what you're going to do is you're going to restrict it with that epsilon value. So epsilon restricts it here and here. And what you're trying to do is restrict this value of 1 so that every single X value has an output on the graph.
Okay, so that like, so if it runs over, like, let's say it was this one, if it, okay, I get,
so
yeah.
like the idea is if it looks like this, then you still have X values that aren't accounted for and don't
and
have
you
an
need
output.
to restrict them right there.
Right, and so you would restrict it smaller. I mean, generally you would start here, right? So that every single X value now has an output.
Oh, so that you see an output. Okay, that makes, see, I wasn't getting that. It wasn't connecting for me. Thank you.
You're welcome.